Alrighty, guys, can you hear me again?
Yes, we can hear you.
All right.
Hear you.
Ready for round two?
Mhm.
Let's see. I should also say, probably all of you already did this, but just in case you didn't, if you haven't signed up for a time slot, please send me an email about it. If you have signed up for a time slot, can you just double check on the website that I didn't mess up your time slot? And if I have, you can just send me an email and try to work it out. There are only 2 days this time for the exams, and this is because it seemed like all the students didn't want to do it towards the end. And so I asked Anna what time slots I could have, and she gave me those 2 days. It seems like every other day that there will be other exams that you guys need to take. So we only have these 2 Tuesdays. So they're going to be long days. Okay, let's do the second half of today's lecture. Right, so we're going to be spending quite some time talking about the interest rate swap. Right, that's of all of these, the interest rate swap is by far the most important. I'm going to give Xiao some numbers to work on, and so here this you should see the TA session for more. I have some data, little spreadsheet exercise, and I'll have Xiao go through it in one of the remaining TA sessions. Right, so there's no TA session on Wednesday, but maybe the week after, we'll have Xiao go through a problem where you do a calibration of you do a calibration of the model based upon these interest rate swaps that we're going to be talking about now. Okay, so the swaps. Swaps have there are 2 legs. There are 2 legs. I should say here that the swaps referred to as either payer or receiver. So a payer swap receives the fixed payment, the fixed leg. Okay, so there are 2 legs. There's a fixed and a floating. So the fixed leg so if it's a payer, it's just a question of being long or short. A fixed leg, well, you're going to receive K at times 1 to then all the way up to say M, which I want to picture. This here is M, which there's going to be a payment of K here. And there's going to be a payment of K everywhere from time 1, time 2, time 3, and so on. You're going to have these M payments. The fixed, because K here is a constant. So K is a constant. This is going to become the swap rate. Right, so the value of the fixed leg at time 0, the value of the fixed leg at time 0, right, you have to move all these payments back here and add them up. That's the fixed leg. Then there's the floating leg or the variable leg. There's a variable or floating. So this is this is the payments there are not going to be constants. So you're gonna, right? So if it's a pair, you receive K, but you could equally well pay it. That would just be the opposite, right? You receive or you pay. And so in this for the floating leg, it's the opposite. So if you're receiving up here, you're paying here. And then, of course, if you're in the red case, you will be receiving here. So now what you're doing is you're paying, and the thing you're paying is stochastic. That's why it's called floating or variable. You're going to pay, and then it's going to be this R n minus 1. You're going to do this at time n equals 1, 2, up to m. So that's the interest rate, which is stochastic in this model here. So now if you look at the picture, you're looking here, for example, at time m, or 1, 2, 3, and so on. The payment that you're going to get here at time 3, this is going to be R2, and it might be that big, and then this one here might be much bigger. This is then Rm minus 1. The payment at time 2, this is going to be R1, it might be big, and this might be very small. So now you see you have stochasticity, whereas up here, the height of all the legs here is the same. Here they vary in height. And so if I want to know what the value of the floating leg is, I need to move these now random payments back in time. Back to time 0. And then the constant up here, the fair swap rate, K, is set such that the value of the fixed leg is equal to the value of the floating leg. So this constant here, that fixed payment that you get over here in the fixed leg, that constant is picked, set such that the value of the two legs, they match up. So that's an interest rate swap. Comments or questions before we start analyzing it? Okay, then let's give it a go. There are two legs we have to analyze. So let's figure out what is the value of the fixed leg. That's the easiest one because you're just going to get these k's. So because k is a constant, getting k here at time 2, you just multiply onto the 0 coupon bonds that go from 0 to 2, right? And then you have the same thing for that one. That'll be k of b 0, 1. And then the last one will be kb 0 m. That would be that value, and this would be just, of course, k, and then the sum over 0 coupon bonds from time 1 to time m. Just something about rotation, like this thing here. This is often called an annuity. So it'll just be denoted by AM. It's just a portfolio of zero coupon bonds. So that was the value of the fixed leg. So that was the easy one. And you see that's going to be linear in K. Ultimately, we want to solve for K, right? That's, you need to find that value K such that this number here, this is the value of the fixed leg, is going to be equal to the value of the floating leg. So the floating leg is the next one. This is the harder one. So the value of the floating leg. Well, we're going to work backwards. Right? This is our picture. We're going to start out here, moving this payment back to time m minus 1. So at the end, we're going to get, at the end, we're having the payment R, right, this was R m minus 1. This is what we get at time m. R m minus 1. And that's the payment. And this here is, this is f m minus 1 measurable. So if I'm moving this payment here, this one back, that's easy. So the value of this thing at an earlier time at m minus 1, because it's fm minus 1 measurable, we just multiply it onto a zero coupon bond, and it'll take us back. It'll take us back to so m minus 1 and m. This is the zero coupon bond that goes from m minus 1 to m. I just multiply it onto r m minus 1. That's because you have this measurability property. Okay, so at time at time m minus 1, we also get a payment. At time m minus 1, we also get the payment. So at time we're going to get R m minus 2. So that's the payment. And then we have this value plus this B m minus 1 m R m minus 1. Okay, so now we want to move this thing back to time m minus 2. And so how do we do that? Well, we're going to use how do we move this thing back in time? We're going to use the relationship between this thing here and the interest rate. So we're going to use, there should be a formula for B m minus 1 m. I know what the interest rate is over the next period, so this is going to be 1 over 1 plus R m minus 1. So if I plug that in, I mean, I could, what could I do? I could isolate like I'm missing a term. let's see. Okay, let's see if I can get this straight out. So this thing here is the same as saying 1 plus Rm minus 1 times B m minus 1m. This is equal to 1. This is the same as saying Rm minus 1 B m minus 1m. This is equal to 1 minus the zero coupon bond. Right, so this expression up here, I can write it as that. This part here becomes 1 minus B m minus 1 m. So the value that I have at time m minus 1 is going to be the payment that I get, plus this thing. This thing here can be written as that. Okay, so now I'm interested in moving this back to time m minus 2. So value at what would that become? Well, 1 plus this guy. This is already measurable. So I'll just multiply up with the zero coupon bond price. I'll get m minus 2 plus the 1. And then I will move it back from time m minus 1 to time m minus 2. And the other term, this is minus the zero coupon bond. Okay, so what is the value of a zero coupon bond? Well, I just plug in the value at an earlier time, b m minus 2 m. As before, we have this relationship between the zero coupon bonds over the next period. So here it was from m minus 1 to m. Here's from m minus 2 to m minus 1. So this thing is going to be 1 divided by 1 plus, and then the interest rate that works from m minus 2 to m minus 1. This is r m minus 2. And so we see d neatly cancels out. This is exactly equal to 1 minus b m minus 2 m. Right, and so we keep doing this, and we move. So we have the value, then we're going to get a payment. Then we move this payment back 1 period. So now we have the value at time n minus 2. Now we're going to get a payment at time n minus 2. And then we're going to move it back, and it's going to keep going like this until we get the value at time 0. So there's no interest rate payment. Right, when we look at our picture up here, the first payment that we're going to get is at time 1. We're not going to get any payments at time 0. So you keep going like this all the way back. You see m minus 2, it's what appears here. So you'll get that the value is 1 minus b, and then this here will be 0 m. Okay, so now we have the so to get the swap rate, we solve. We match up the two legs. This was k times the sum from n equals 1 to m b 0 n has to be the same as 1 minus b 0 m. So this is the same, saying that k is 1 minus b 0 m divided by the sum. Should we do this one more time just to make sure we got it? So we're looking at the floating leg, and the floating leg pays out these payments that are given by the interest rate. And what's important is that the payment you get at time m, it's going to be given by Rm minus 1, right? So the payment you get at time 3 is going to be F2 measurable. So it's easy to move this payment here back one time, right? If I wanted to move this R2 payment just back to time 2, if I were to just move it from here to there, then the way that I would do that would be to say R2 times, because this is already F2 measurable, I can just multiply it onto a zero coupon bond that works between 2 and 3. So I can move this R2 payment from time 3 back to time 2 simply by multiplying onto the zero coupon bond. And of course, I can use that this is equal to R2, and then I can use the formula for the zero coupon bond. This is 1 over 1 plus, and then it'll be R2. So it's this calculation here I'm using. This calculation I'm using over here. How do I move the last payment from time m to time m minus 1? Well, I multiply onto the zero coupon bond. So the value of this payment here at time m minus 1, the value of this payment here at time n minus 1 is just going to be multiplying onto the zero coupon bond. So what is the total value I have at time n minus 1? I also get the interest rate payment, and then this value I have here. And so now what I'm interested in moving this thing here back to time m minus 2. And so how would I do it? Well, the first one is easy because it's already f minus 2 measurable, but this one here is not. So we use the connection between zero coupon bond and interest rates. And so you can write this last payment here as 1 minus this zero coupon bond. And so what you do is when you want to move it back once, now you have Rm minus 2 plus 1. That part, it's already Fm measurable, right? This here will be written as Rm minus 2 plus 1. This quantity is Fm minus 2 measurable. and the other part minus, then this is the zero coupon bond. This here is a price process, right? So if I want to know what value this thing here has at time m minus 2, I just multiply this quantity onto the zero coupon bond. If I want to know what this value here is at time m minus 2, well, it's a price process. I just look at the price process at that earlier time. So overall, when I do this trick, right, I'll move the first part simply by multiplying onto the zero coupon bond. I'll move the second part simply by inserting an earlier time point into the price process. And so I get what I have up here. And then I just continue the mechanism. I'll use the relationship between the interest rate and the zero coupon bonds, and then I'll just keep going like that. You keep iterating this, and ultimately you get to an expression like this one. That's the value of the floating leg.
Hello, Professor. I want to ask why the value at m minus 1 should add the rm minus 2?
Because that's the payment you get. Right, at time m minus 1 here. This is m minus 1. What payment you get? You're going to get this payment that is rm minus 2. Right, so to find the total value you have here, you're going to take this payment plus the payment you get out in the future. This thing here has to move back, right?
I see. Thank you.
So this value here, and what we're looking at here is we're looking at the payment you get out of time m. This is this rm minus 1. So that's the first thing we do, right? We're going to move this payment back here. That's that guy. And then we're also going to get a payment here, rm minus 2. So we're going to move the payment from the future back here plus the current payment. And that's what you see here. Other questions, comments on this? So I wanted to show a little example on how one could go and calibrate. So the formula that we need to remember is this one here at the bottom. That's the key formula for the swap rate. So let me look at problem, I think it was number 18. It's also an old exam question. This one here. This one here. So we have a swap. And so there are these two legs, fixed and a floating. And you're given swap rates for 2 maturities, a 1 year and a 2 year. And so the question is, what are the corresponding zero coupon bond prices? So this is how the interest rate models here typically calibrated. This is number 18. Let me write it down. This is when I talked about calibration in the beginning. This is what I mean. So say you have 2 swaps trading. So there are 2 maturities. M is equal to 1. M is equal to 2. So we're going to have the fair rates. The fair swap rates are given by 5%. So this is the M equal to 1 maturity. And the other one is a 10%. So if you look at the fixed legs, you have M equal to 1. Right, so we're sitting here times 0. maturity is 1, you're going to get $5 out here on a $100 notional. This is on a 100 notional. For the swap that has 2 payments in it, the picture is you'll get something here, you'll get something here. Remember, it's always for the fixed leg, it's always the same height. There'll be a payment here, and there'll be a payment here. And then you're sitting out there. And the payment you'll get here is $10. And this is again on a 100 notional. So this is what you're given. You're given that the fair rates are 5 and 10%. And your job is to create the 0 coupon bonds. How would one go about doing that? And this is what calibration is. So calibration is about observing here K1 and K2 and backing out, in this case, B01 and B02. How would we do it? Well, we will use that formula. So we will use that K1 is equal to 1 minus B01 divided by, well, B01. So this is one equation and one unknown. And so you know that this here is equal to 0.05. So this is one equation and one unknown. You can solve, you'll get B01. If I did it correctly, it's 0.952. So you observe what the fair swap rate is, and it'll tell you what the first 0 coupon bond is. And then you can move on. You also know that K2 is equal to something specific. Right? The formula here is the one we're using. So you have 1 minus B02, and now you have to divide by 2 0 coupon bonds here. So you have the K2 is equal to 1 minus B02, and now we have to divide by B01 plus B02. But then you plug in, this here was given to be 10%. And you can use the previous answer. So you write this as minus 1 minus B02 divided by that number up there, 952 plus B02. So you get another equation and one unknown, and you can solve. Pending my ability to solve one equation and one unknown, you're going to get that this is 0.823. So in practice, you can observe swap rates for many different maturities. So this will be like a month, a quarter of a month, half a year, 1 year, 2 years, 5, 10. I think it goes up to 15, 20, and 30 years. You also observe, so this is, these are, there's no default here. So you can also observe swaps written on companies, or you can even you can also use like states, like not New Jersey. You can also have countries here. So these involve default risk. Which is different from what we have up here. Right? What we had in our setting is that you will get these payments for sure. You're going to get these $5, $10, and $10 here. There's no chance of default. It's not like the guy who promised to pay these $5 and $10. He has the possibility of going default, but in practice, you do have this default risk, right? So we're going to get what's called a credit default swaps, or CDS. And there is there's a similar relationship that one can derive as what we have here. Right? So we're not doing that. So we're looking at this top part here. This is just a note down here. But the standard mechanism for calibrating fixed income models is to look at the swap rates, and then based upon the swap rates, you will figure out what the zero coupon bonds are. Are there any questions or comments on this one? Are we good?
Yes.
So now we can start playing some tricks on top of this. There are variations of this swap that we've been looking at here. Some of them are so let's look at some variations. They're not big variations, but there are some variations. So a popular variation of this is a forward starting swap. So it's not quite the same, but it's very similar. The forward starting swap, right? So we have the maturity of the swap. This is the swap's maturity or expiry. But the difference is that there's also a beginning point. It's like an M0 here. This is when the swap starts. This is the swap starting point. And then we have over here, if this is time 0, we could have, how general do we want to do this? Maybe we should just say we start out here. This is today. So there will be no payments coming in between here. And then what's going to happen here is we'll have the fixed payments. So we'll have the fixed payments. Okay. So this will be at time m0 plus 1, m0 plus 2, and so on. So at time m, it's just a standard swap. At time m, then it's just this is just a standard swap with two legs. So you're gonna have the fixed leg. You're gonna have the fixed leg. What's the value of the fixed leg? That was the one we had before. This will be k times the sum. So we're going to be summing here b. So this is going to be b. We go back to time m0 and we go out n. So this is going to be from n equals m0 plus 1 to m. And then we're going to have the floating leg. And that was the same as before. This is going to be 1 minus, and then it'll be b m0 m. So this was at time m0, but if we are sitting here today, so then we move them back to say time 0. Move back to time 0. So then we're going to get, when we have two legs, we'll have the fixed leg. Fixed leg, now we're just going to move it back to time 0. So that will be k sum. Then instead of the value of the zero coupon bond at time m0, it'll just be the value of the zero coupon bonds at time 0. And the same thing for the floating leg. We move $1 back. This is going to be b. When is the $1 coming? It's coming at time m0. So this is going to be b0 m0 minus b and then 0 m. So the fair forward starting swap rate, that fair forward starting swap rate is going to be equated to k is equal to that difference, b0 m0 minus b0 m divided by that sum from m0 plus 1 to m b0. The fair forward starting swap rate. And of course, when m0 is equal to 0, they coincide with the standard swap. So this was one variation, the forward starting swap. Another variation is the swaption. Another one is the swaption. So what is the swaption about? So let's look at a picture. So here there is a point m0 as before, and now there's an expiry. This is m, and then there's the today point. So as before, this is the swaps expiry, and this one here is today, and this one here is the option. Actually, there are a bunch of different time points that are important. This is where we're sitting. This is where the option expires. And this here is where the swap expires. Okay, so we're looking at an option on a swap. This is the swaption. So this is an option to enter a swap at time M0. So we have the option to enter a swap at some future point in time. Let's denote that by M0. Okay, so what's the payoff? So what is the option? This shouldn't call it option, I should call it a swaption. Swaption payoff at time M0. Okay, so let's figure out what is the fair. So let M0, let KM0 denote the fair swap rate at time M0, right? So that's the one we had. That's the one we had. Where was he? That was this guy. So when you have what is the value of the two legs that match up? So this is my K, and let me denote that by KM0. So KM0 is such that these two match up. So this is 1 minus B M0 M divided by the sum. So that's the fair swap rate at that time, right? So we have the option to enter a swap at time M for strike K. And K here is a constant. So the fair swap rate at time M0 is given by this thing. And now we have the option to enter it for the strike K instead. Okay, so the payoff that we're looking at, what we're going to be doing is we're going to be looking at how does K compare? How does K compare to the fair rate, KM0? And then, so we're looking at this thing here. This will be like a put. So we take the positive part, and this will be the payments. Then when we're receiving, when will we be receiving these payments? We'll be receiving them at later times K. So we add time M0 and then N from N equals M0 plus 1 to M. So this is the payoff. This is the swaption payoff at time M0. So just to put some numbers on it, this one here, this is a constant. That's the contract case. That's the strike that's within the swaption contract that you can exercise at. And then this one here is this is stochastic, right? This is the fair. This is the fair swap rate. Right, so this is stochastic. And in these ones here, zero coupon bonds, we had many times before. Right? So that's the swaption payoff when the option expires. So now we want to take this payoff and move it back to time zero. And so we do that by discounting. So the value of the swaption at time zero, well, we discount the payoff and compute the risk neutral expectation. So the payoff is coming at time m0, so we discount it back from time m0. Then the payoff, k minus k m0 positive part, sum So if you want to price swaption, you need to compute what this expectation here is. And Km0 is this ratio up here. Any questions or comments on this? That's a swaption. And the one we have here, this is like the put structure. You can, of course, swap the two roles of Km0 and K, and then you get more like a call structure on the swaption. Maybe one thing to note here is that there is actually, so you often see this written in terms of a measure. It's called QN. And QN, the way that it works is you have discount factor and you have zero coupon bonds. So you know that when I discount with the money market account, when I discount the zero coupon bonds, I get a martingale. So it's often written in terms of a measure QN with Radon-Nikodym derivative process. So this is going to be my Z, and this guy is defined by, I should call it N here. What should I call it? I need another letter, K. K doesn't work because I have K's up here. What are we left with? I, maybe an I. I could put an I here. Okay. Impossible to read. C and I. And so what I do is I take my zero coupon bonds, B, I, N, I discount them, C is 0, I, and I sum them up over N, going from M0 plus 1 to M. And these are all martingales because I discount the zero coupon bond price, I'm going to get a martingale. And so if I normalize them, so what are the expectations of these things? This is going to be the sum of B0N from n equals m0 plus 1 to m. That's my z. It looks pretty complicated. But what I'm doing is each component in the sum is a martingale. A sum of martingales, I get a martingale. I normalize it so it starts out at 1. C and 0 is equal to 1. Ci and it's a martingale. And then I can write, and then we can write, the swaption price as I need to put in the Radon-Nikodym derivative. So this is my C M0 and so I'm going to absorb this part and that part into a Radon-Nikodym derivative process, and then I need to multiply up to the zero coupon bonds, 0 and n equals m0 plus 1 to m. And then I'll have my difference, k minus k m0 plus. And now this is a constant. You can go outside and do the change of measure. This will be the expectation now under this q and of k minus km0. So this is a formula, and my zero coupon bonds have been out here. This is a formula that you will see quite a lot. And what you have here, this is v and 0, the value of the annuity at time 0. And this measure here, this is called the annuity measure. So you'll often see swaptions being written in terms of the annuity measure. And so k here is a constant. So what you need to know is you then need km0's distribution onto this measure q and. Because as soon as you know what this is the only random variable that's left, as soon as you know what that distribution is, you can compute this expectation, multiply it on to the sum of these zero coupon bonds, and this will give you the swaption price. Are there any questions on this last slide here? So we looked at two variations. We looked at a forward starting structure, and then we looked at an option written on. Looked at an option written on the forward start or on the swap, and the option comes in with these pluses here. We did quite a bit. We did options down here. So we have floors and caps, and we have options on zero coupon bonds that are left, and we got about half an hour left. So I think we can get through it. Let's do options first. Let's do options on zero coupon bonds. So let's do options on zero coupon bonds. So now the picture is the picture is we have M, we have this M0, and say we have N. Maybe this is 0. So this part here, this is when the zero coupon bond expires. M0, this is when the option expires. And this here is today. Maybe we can take today just make it easy and move today to be a time 0. So we have an option on a zero coupon bond. We want to price it. So we're going to be looking at the option payoff. This is at time M0. What does the option look like? Well, if it's it can either be a put or a call, maybe we should look at a call. It would be B M0M minus a strike. It could be a put. Then it's K minus B M0M. So this is the payoff at time M0. So we want to move it back to time 0 if this is where today is. So the value at time 0, well, we look at the difference, B M0M minus K, positive part. And so we discount it. If we're going back to time 0, we're going to discount it by the money market account. The payoff is coming at time M0, so we need to discount it back. And the money market account value at time M0, and then compute the expectation under the risk neutral measure. So we can write this here as, the way to do this is to write this as, we'll break it up. So we write this as 1 over S0 M0, and then I'll remove the plus. I'll remove the plus, and then I have to put an indicator that I'm in the money. And now I can work out two terms. I can work out the first term. This will be the expectation. BM0M divided by the money market account times the indicator for being in the money. And then minus, and I have my K. K is a constant. You can go outside. This one here is a constant. Right, this is the strike. I have my K. What else is left? The expectation under the risk neutral measure of 1 over SM00, indicator for being in the money. So I have these two terms, and it's custom if you are to work with a model that prices zero coupon bonds. These two terms here, they can be re-expressed in terms of the forward measures. So we can express these two expectations in terms of forward measures. This is from last time. So remember the forward meshes, these are the ones that have the radical derivatives. So you have dp tilde, what do we call dp tilde, say m, the radical derivatives. They will be defined through 1 over the money market account, and then normalize it with the zero coupon bond. So here we have the radical derivative. This is for m equal 1, 2, and so on. And these are the forward meshes. Right, and this was when we were talking about the difference between forward and futures. Well, you see if the radical derivative is equal to 1, when does that happen? Well, for example, if the interest rate is deterministic, because what you have down here is exactly the expectation of what you have up here. So we can use these forward meshes to calculate these two terms. Maybe we should start with the second one, because you can see here is the radical derivative already. So for example, if I were to write k and then this expectation, 1 over SM0, the indicator being bigger than k, I can write this in terms of the radical derivative. All I need to do is divide by the zero coupon bond. And then of course I'll have to multiply out with the zero coupon bond. And by doing that, I get that this term here, this is exactly the radical derivative, dp tilde m, dp tilde. And so I'm stuck here with k times the zero coupon bond times the expectation, not under the tilde measure, but under this forward measure. Just make sure I get the indices right. There's a 0 on the M0, so there should be a 0 here, and a 0 here, and a 0 there. And then this indicator. Right, we know that the expectation of an indicator, this is the same thing as the probability. P tilde M0 of the zero coupon bond being bigger than k. So this was one term. If we want to do the pricing, we also have to get the first term. And the first term looks a little bit more complicated, but it's really not that bad. Another thing we know that there's a martingale structure. We know that this object here, the zero coupon bonds divided, these are martingales. This was one term. The second term is we're going to note that B, so say BI M divided by this I, this object here. This is a P tilde martingale, and when I put in I equal to M, I'm going to get a 1. So let's see if we can use these two properties to work out what the first expectation is. So I'll use iterated expectations. Okay, so let's try to work out what this is. I know it's a martingale, so what I can do is I can put in an extra expectation. So I'll write here B, and then I'll write M and M divided by SM0. So if I want to get this term here to be the first one, I need to condition I need to condition. I need to condition on if M0. Yeah, this is good because this is exactly the martingale property. When I compute this conditional expectation, I'm going to get the first term. Then I'll leave the other one. This is bigger than K. Now I'll use this quantity here. This is if M0 measurable. Right, so this can go inside the conditional expectation. This can go inside the expectation. This is a 1. As the indicator that BM0M is bigger than K. It's a lot of writing, but MM, this was the property here, that was a 1. So we put a 1 here instead. This quantity here is measurable, it goes inside. And so now what I'm stuck with here is, the expectation of a conditional expectation. We can throw away the conditioning, we'll be left here with E tilde 1 over SM0 times BM0M bigger than K. I messed up some indices here. Gotta be careful with these indices. MM, this condition here, this is a martingale, there should be no 0 here. Should be no 0 here. So use the martingale property. So when I condition here on M0, I'm going to get exactly what I have in here, but with M0 here and M0 here. And M0 here and M0 here. That's good. Right, and now we have the same situation as before. If I want to write this in terms of an analytical derivative, I'll divide here by B0M. I'll multiply on to B0M. I'll then note that this quantity here, this is the analytical derivative, dp tilde m dp. And so as before, we're going to get that this is B0 M times P tilde M of being in the money. So now we have the two expressions. We have this one, and we have this one. We should just note that we are working on the two different measures. This is M0, and this is M. This is M0. This 0 up here comes from that 0 down there. So what you need, to compute options on 0 coupon bonds, you need B0 M0's distribution under P tilde M and P tilde M0. Right, these are the forward measures corresponding to 0 coupon bonds that expire at time M and then expire at time M0. questions or comments on zero coupon bonds and options? So if you're looking at models where if you have a model where you want to price, maybe you should step back a little bit. If you have a model where you want to price options with non-swaps, well, then what you want to do is you're going to prescribe dynamics under this annuity measure, because that's the expectation you need to calculate. If you're looking at a problem where you want to price options written on a zero coupon bond structure, well, then what you need to prescribe is distributions of zero coupon bonds under the forward measures. Those are the relevant measures that you need to calculate expectations on. Are there any questions or comments? Okay, let me just write the last few things then to wrap it up. The last thing that we need is caplets and floorlets. Caplets, well, so caps are portfolios of caplets. So a caplets, so the payout at time n, the payout is R n minus 1 minus a strike. So it's an option. In this case, it's a call option written on the interest rate. And so floorlets. So floors, the portfolios of these floorlets. So at time n, the payoff, you just swap them. You're going to get K minus R n minus 1 positive R. So a cap is a bunch of these for different expiry dates, and floorlets is a bunch of these at different expiry dates. There was something called a collar. Collars. They are linear combinations of caplets and floorlets. So you could, for example, have something like Rn minus 1 minus a strike, K1, and maybe minus K1 minus, or maybe K2 minus Rn minus 1 positive R. So this here is the time and the payout. And so we can be interested in pricing these ones, and it's going to go through the same machine as what we did before. You can note here, so for example, to price them, you can note that this one here, this is at time n, so you can note here that the payoff of this quantity, Rn minus 1 minus K, this is if n minus 1 measurable. So the price, the time n minus 1 price is B n minus 1 n times Rn minus 1 minus k positive part. And then you discount this back to time 0. So then the time 0 price would be an expectation 1 over is, now we add time n minus 1, so this is n minus 1 is 0, and then this this expression. So that'll be one way to do it. You can also, alternatively, you could use a connection here. You could write that the zero coupon bond at time n minus 1 n, this can be written as 1 over 1 plus r n minus 1. So you can write here that what would be r n minus 1 is equal to 1 over b n minus 1 n minus 1. So you look at, if you look at the Caplet's payoff, which was r n minus 1 minus k positive part. Well, you can write here, instead of Rn, you can write this as 1 over b n minus 1 n minus 1 minus k positive part. And then use the first part, multiply through with b here. So then multiply through with, so the value of n minus 1 is going to be, you have to multiply onto that zero coupon bond, b n minus 1 n, multiply through r n minus 1 minus k positive part. So if you multiply this thing through, like it will cancel out this one here, you'll have 1 minus, and then it'll be k plus 1 times b n minus 1 n positive part. Right, so this here is an option. This is an option on a zero coupon bond, which we already did. So these caplets and florets and collars, they can also be viewed by doing this little trick here. They can be viewed as options on zero coupon bonds. And so if you know how to price options on zero coupon bonds, it doesn't take very much to figure out what the price is of a caplet and a floret. Alrighty, this was a lot about fixed income today. Are there any questions before we say goodbye?
I want to ask some questions on our textbook.
Okay.
Firstly, I wonder what this means. What's this signal means? Let me open the camera. Oh my god, I can't see my camera. Why? Okay, I can see it now. Oh my god. Oh. This. What does this mean?
Unions and intersections.
Is that basically an intersection and then union and then intersection?
Yes. Unions and intersections.
Union. Oh. which means that the the an intersection union am intersection.
Well, you have three operations in the front, right? First you do intersection, then union, then intersection.
Okay. Okay, and then this, and then this. This I want. This I wonder why.
It's the length of the interval.
Why this is the length of the interval?
Well, your mu x
Mm,
is probably the Lebesgue measure.
mm,
Does it say that anywhere?
mm.
I can't read that quickly, but if you look at the length of that interval, k divided by 2 to the nth and k plus 1 divided by 2 to the nth, if you look at the difference between these two endpoints, you're going to get 1 over 2 to the nth.
Oh, I see, thank you. And I will.
Yeah, other questions or comments?
Professor, after the last week of classes, will we have additional office hours prior to the final? I'm just wondering if if I should prepare all my questions for that last week of class, or if there would be more.
So the exams are going to be on the 15th and the 22nd.
Yeah. And I think the last week of classes is like after December 4th. December 4th should be the last, I think.
I have it in my notes to say the last class is the 8th.
Oh, the 8th? Oh, okay.
Let me just double check. So Rutgers calendar. Rutgers calendar says that regular classes end on December 10th.
Oh, I see. Okay.
I should check with Anna just to make sure that the MS/MF program is on the same calendar, but I think it is.
Yeah, my bad. Yeah, so I was just wondering, will we have office hours after that, or would that be our last opportunity to ask you questions?
So I need to hang on because I have the other class where I have all exams, and I need to see when they are scheduled for.
Okay, yeah.
Hang on just a second. I'm clicking through all my notes here.
Okay.
So that Thursday, the 10th, this is going to be the last day because I start having all exams on the next day, Friday, the 11th.
Okay, so your Thursday office hour would exist on that day.
Yeah.
Okay, yeah, that's great. Thank you so much.
Okay.
Okay, bye.
Bye. Alrighty, guys. I will see you next week.